Well, hello and good morning for another wonderful fun-filled day of 307. Today we're going to be going over some steps, concepts, and skills for solving material balance problems. We're going to be focusing on single unit operations today. Next Monday, we'll start looking at more complex material balances involving multiple unit operations. Before we get started, just a quick friendly reminder, your first homework is due tonight by midnight, and your first quiz is due Sunday by midnight. So don't forget to get those into Blackboard. The quiz is done on Blackboard. It is timed, so make sure you're gone through the material and you're comfortable before you begin the quiz. Before I get started, does anyone have any questions about what we've discussed thus far or any sort of major issues they're having? Yes, no, maybe so. No? Okay. Well, let's go ahead and get started. So what we're going to be looking at today is material balances with single unit processes. Now, looking at a simple process, we have some inputs, maybe some outputs, and depending on the nature of the problem and the number of components in a system, even these single unit processes can become fairly complex fairly quickly. And so it's important to have a stable and reliable method for performing these material balances such that you don't get lost, you don't get confused as you look at more complex systems. And so one of the big things that we emphasize is having a sound solution strategy. And that means the first thing you want to consider when looking at a material balance problem is developing a flowchart. So I'm going to say step one, develop a process flowchart. We really call these block flow diagrams, but we're not in terms of as picky as we would be for a block flow. But that's really what we're trying to develop and do. And so the key thing with a block flow diagram is it's a good way to digest a complex problem and lay it out in a simple and visual manner so that you get an idea in terms of what are your unknowns, what are the givens, what are the things that you need to look up, and what are the assumptions that you need to make prior to performing any calculation. Also, it's important when looking at process flow sheets and flow charts and ask yourself, is the problem solvable? And the way you do that is by looking at a degree of freedom analysis. And a degree of freedom analysis is a good way of figuring out, what are the number of unknowns, what are the givens, what are the equations or the relationships between my unknowns, so that I can ask and answer the question is this problem solvable, or do I need more information and more relationships to make it solvable? So let's talk a little bit about flowcharts real quick first. So let's look at this example here. Can you guys see the PowerPoint slide, or are you guys only able to view my notes sheet?
Only the note sheet.
Okay, I gotta tweak some settings and zoom then. How do I do this? Oh, it's because it's still sharing. It might be easier to do this. If I just share my screen, it'll be easier to jump back and forth. So looking at this example, we have a problem given that states a stream of air, 21 mole% oxygen, 79 mole% nitrogen, a stream of pure oxygen, and a stream of liquid water are flowing at a rate of 20 cubic centimeters per minute, being fed into an evaporation chamber in which it all evaporates. It states the flow rate of pure oxygen is 20% the flow rate of air, and the emerging gas contains 1.5 mole% water vapor. So the question then is, what is missing and how can we add a little more detail to this flow chart to make it easier to understand and make the unknowns a lot more apparent? Well, let's take a look. We've got an evaporator here, just for organization. We have an evaporator with 3 input streams. We have an oxygen, we have air, and we have a water stream. And then we have our output, which is the mixture. Now, as provided, we have to ask ourselves, what are the knowns in the problem and what are the unknowns in the problem? So going back to that flow sheet, well, the biggest things that we really don't know are we really don't know any of the flow rates. And so what we could do is we could say this is a certain molar flow rate in N1, this has a certain flow rate N2, this has a certain flow rate N3, and then the outlet has a certain flow rate N4. In addition to those total molar flow rates, we can consider the components within each of those streams. Now, for this example, the oxygen stream is pure, the water stream is pure, but the air stream is a mixture of oxygen and nitrogen. So I can add further information on the air stream that states that for my O2, it's 0.21, that main flow rate, and for my nitrogen, it's 0.79, that flow rate. And I can do this, O2, this is H2O, and then I can ask myself, well, I have a mixture leaving the system, but I don't know what those component mole fractions are. So I can do one of two things, which here, let me clean this up to make it a little easier. So this is going to be N3O2 N4. I can say, well, I have an X unknown, flow rate of nitrogen, a Y molar flow rate of oxygen, and a Z molar flow rate of water vapor. So looking at this problem, I begin to ask myself and kind of, start to panic because there's a lot of unknowns in this problem. And so you start to ask yourself, is it even solvable? Then what you can consider are the relationships provided in the problem to reduce the number of unknowns to make sure that everything is as specified as given in the problem statement. For example, in the problem statement, I need to just put this somewhere. It states that the oxygen stream is flowing at 20% the flow rate of air, meaning I can relate my oxygen stream to my nitrogen stream. So I can rewrite the expression as I have it. Instead of saying an N1 and an N2, I can say this is going to be 0.2 of a flow rate, and it's related to this flow rate. And so if I write it like this, I've reduced the number of unknowns using the relationship as specified in the problem statement. Further, the problem also states for my water flow rate, it's given in terms of a volumetric flow rate of 20 cubic centimeters per minute. So I can include that here and say the flow rate is 20 cubic centimeters per minute. And knowing the density of water and the molecular weight of water, excuse me, that should be water, not oxygen, I can solve for that lower flow rate. So this can be calculated. So looking at the problem statement and developing my flowchart, I can reduce the number of unknowns in my problem and make my calculations more apparent and much easier to solve. Does that make sense? Are there any questions? All right, and to finish this up, it also did state some information about the water in the final gas stream. It's 1.5 mole percent water vapor. So I can clean up these unknowns. And if this is 1.5, this is 0.015 in terms of the mole fraction, which makes, if this is an X for N2, my mole fraction of oxygen is simply 1 minus the mole fraction of water, or 0.985 minus that X. So I can say 0.985 minus X. And so now, instead of having those 3 unknowns, I simply have 1 unknown. Are there any questions on this problem and example in developing flowcharts? I strongly recommend you develop flowcharts for every problem you do. Some problems on the homework and on the exams will require flowcharts, but I won't require it for, or it won't be a required or graded portion for some problems, but it's still good practice to do for developing material balance. Because as I said before, as these get more complex, using a flowchart makes it a lot easier to identify what are the givens, what are your unknowns, and what are the relationships that I need to solve my material balances. Right, because I went from, I think, 5 or 6 unknowns down to, let's see, how many unknowns do I have here? I got 1 for the N1, 2 with N2, and then 3 with X. So now I only have 3 unknowns, which I have 3 components, and with 3 unknowns, that means this problem is specified and I can solve it. All right. All right, now let's talk about considering a process that's balanced and considerations for scaling. If we have a process, let's say we're mixing a couple components. See, I have 5 kilograms C6H6, 3 kilograms C7H8, and the final output would be 8 kilograms, 5 kilograms C6H6, 3 kilograms C7H8. I can state for this process that it is a balanced material balance or a balanced process. And a process is considered balanced when all system components are specified by a material balance. Meaning, if you perform a material balance on every component and everything's been solved and the material balance holds in your system, the overall process can be considered balanced. And what that allows you to consider is opportunities for input manipulation. Meaning, I can take this same process and instead of having 5 kilograms and 3 kilograms, I can have 15 kilograms C6H6 and 9 kilograms C7H8. This would give me 24 kilograms out with the same amount of components. I've increased my throughput through the process. I know that's terrible handwriting, I apologize. But the structure and nature of the material balance hasn't changed. The only thing that's really going to change when we're looking at that are the actual specifics of the process itself and any sort of energy transfers, inputs and outputs that occur within the process. But the material balance is largely the same. What we've done is simply scaled the process, which is essentially multiplying the overall process by a common factor to either inflate numbers or increase production if this was a chemical process, or deflate or lower production. So I can call scaling manipulation of a process material balance by a common factor to increase or decrease. It's really hard to write on these amounts and or flow rates. And so scaling becomes important when you're looking at throughput for a given process. You'd like a given process to have the flexibility of having an increase or a decrease in production depending on what's needed by customers, the market, and future demands. And so ensuring that your process is balanced allows you to do quick calculations and estimations for the impact of scaling on your process. Now let's look at a different process, or I could say, let's look at a similar process. let's say I have two components mixing like before, and I have a certain flow rate here, N1, a certain flow rate here, N2, and then another flow rate here, N3. I'm going to have, say, oxygen in this stream, nitrogen in this stream, and then a mixture of oxygen and nitrogen. So I have a whole bunch of unknowns. Right now I have 3 unknown flow rates and 2 components. So the question is, how can I fully specify this problem in such a way that I can solve this material balance? Well, one of the ways I can do that is through relationships and through what's called taking a basis or a basis of calculation. For example, let's say that if N1 is 1/3 N2. All right, I've made a specification for the flow rates of comparison between my N1 molar flow rate and my N2 molar flow rate. So that gets me closer to specifying this problem. However, I still don't know enough information to solve this problem. So what I can do is taking a basis of calculation, which is an assumption regarding a process flow rate or amount that allows a problem to be what's considered fully specified and solvable. Which means if I go back to this process, and now I say I'm going to take a basis, and I'm going to say my basis is N1 is 100 moles per minute. Which means, based on the relationship that I have, N2 is going to be 300 moles per minute. Which means, based on that basis, I can now solve for N3 and say N3 is 300 moles per minute. And now if I wanted to know what is the mole fraction of O2 in stream 3? Well, looking at this, I have 100 moles of N1 going into N3 out of a total of 400 moles per minute going in. So the mole fraction of N2, of O2 in stream 3 is 100 moles per minute over 400 moles per minute, or 0.25. So my mole fraction is 0.25, or my mole percentage is 25 mole percent. How would that change if my basis now was 10 kilograms per hour? Same question. What is the mole fraction of O2 in stream 3? Well, looking at that process again, I don't want to say kilograms. I'm going to say moles. It makes the calculations easier. So I had O2, N2, my mixture, and I said N1 was equal to 1/3 N2. So now I have a different basis, which is 10 moles per minute for N1. Well, if N1 is 10 moles per hour, N2, based on the expression, is 30 moles per hour. And N3, therefore, is 40 moles per hour, which, when I find that mole fraction of O2, I have 10 moles per hour over 40 moles per hour, which is still 0.25 or 25 mole percent. So my basis did not change my answer in terms of that component mole fraction. However, it specified the problem such that I can solve and get a definitive answer. Without a basis specified or an assumption made, the problem as presented is unsolvable. And so taking a basis is a very important technique in solving process material balances, because more often than not, we're interested in looking at molar compositions, mole fractions, and relative rates and ratios, not necessarily total amounts of things or total flow rates. We're looking at relative comparisons. And so taking a basis allows the calculations to be done without influencing the actual answer. Is there any questions on that? Does it make sense? Anything I can further clarify?
A second ago, you said when you were first giving an assumption, you wanted to do kilograms per hour, but you decided to change it to moles per hour and said that it was going to be simpler. Why would it be simpler?
Just because if I wanted to change that, I would have had to calculate. Now, we can look at that if you'd like. So let's jump back to that basis then. What was it? N1, well, it wouldn't really be an N, it would be like an M1, is 10 kilograms per hour, right? So if I had that same process, I'm gonna say M1, now we're looking at things in terms of mass. It gets a little trickier in terms of mass. And I had N1 was 1/3 N2. So in order to take it from a mass flow rate to a molar flow rate, I need the molecular weight, because the molar flow rate is the mass flow rate over the molecular weight. So for oxygen, I have 10 kilograms per hour over 30, excuse me, 2 kilograms per kilomole. So doing that math real quick, I have, let's see, 10 divided by 32, 0.3125 kilomoles per hour. That's why I didn't want it, just because I had to do this math first and it makes the numbers not as easy. But the process continues just as before. If N1 is 0.3125 kilomoles per hour, N2 by the relationship above is 3 times that, or 0.9375 kilomoles per hour, which makes N3 the sum of those two, because it's non-reactive, 3125, or 1.25 kilomoles per hour. And the mole fraction of O2 is 0.3125 kilomoles per hour over the total, and N3, 1.25 kilomoles per hour, or 0.25. That's why, just because you had to do a little extra step and it made the math a little ugly, but it's a good illustration to say even taking a mass basis doesn't change the end result, right? It's just a means to an end, so to speak. When taking a basis, I recommend taking large-ish numbers such that you don't have to worry so much about decimals. That's why I looked at 100. 100's really good. Kilomoles per hour, kilograms per hour, so that when you're looking at component mole fractions that are like, 41% ammonia, in a stream, you take a basis of 100 kilomoles per hour for that stream, then you're just looking at 41. You're not looking at a 4.1, a 0.41. It makes the calculations easier. It makes it easier to kind of think on. So my recommendation is do reasonable numbers, not too big, not too small. 10, 100, 1,000, depending on the numbers you're looking at, are usually good values to use for bases. And sometimes if it helps if you like doing like a basis of 1. Like I said, it really just depends on the problem. And there will be problems where you have to take a basis because without it, the problem is unspecified. So any other questions? No? Okay. So I've been talking about, specified, unspecified, but let's dive in a little bit on that for a second. And particularly when it comes to what's known as a degree of freedom analysis. And so a degree of freedom is a way of determining whether a problem and process is fully specified and solvable, whether there's more information that you need, some assumptions and relationships that are missing to make it a solvable problem. So let's take a look at what degree of freedom analysis is, how it's done, and what it means for doing material balance calculations. So I can say my degree of freedom which we call the DOF. I'll say it allows us to consider the number of unknowns and equations / relationships provided to determine if a problem is solvable. Because if there's too many unknowns and not enough givens, you really can't do much, and the problem becomes unspecified, and it's not solvable because there's no one solution. And so it's important when looking at material balance problems to, after you've developed that flow sheet, excuse me, I don't know why I keep saying flow sheet, too much Excel. After you develop your flow chart, which helps you identify what are your unknowns and what are your relationships, then you perform that degree of freedom analysis to kind of put it all together and answer the question, is it solvable or not? Is there more information that I need? Is there information I have to consider? Are there, process variables, property constants that I have to seek out to make the problem specified and solvable? Those are what that flow chart and what the degree of freedom analysis will help you figure out. And so to solve or determine the degrees of freedom, it's simply the number of unknowns I'll try to rewrite that. Sometimes my pen gets a little possessed. Minus the number of components minus the number of independent relationships, which you can argue the number of components is an independent relationship depending on how you see things. And so, if you perform a degree of freedom analysis and it's 0, then the problem is fully specified. and solvable. If the degree of freedom analysis comes up positive, then the problem is underspecified and cannot be solved. You know, this is the part where you have to consider assumptions and missing relationships. Right? Can you take a basis to make it from a degree of freedom of 1 down to 0? Specifying that flow rate, it may be what's needed, right? That's the importance of taking a basis, because there are going to be a lot of problems when you're most likely going to only be missing you're going to have 1 degree of freedom. And by specifying that basis, you make the problem solvable. On the flip side, if you do a degree of freedom analysis and it comes up negative, then the problem is considered overspecified. You have too many relationships. And you cannot solve this. Something went wrong. Right? It's that blue screen of death, but for your homework. And so you might have to consider, was there redundant information, or where is there an inconsistency? Because that's what most likely happened. One of your relationships that you've identified is in conflict with another, or things that you've considered to be independent relationships, there might be some dependency. And so you have to go back, reinspect your flowchart, and reinspect your values and your relationships that you've identified, and to try to figure out the issue.
I have a question.
Yes.
So you want your degree of freedom to equal 0 always.
Yes.
So if it's overspecified, it's still not solvable as well?
Yes. There's something happening. You've either identified too many equations, or you have some redundancy of information, or there's inconsistency in your relationships. For example, if I say 2x equals 3y, 5x equals 6y, these relationships are inconsistent. And
Okay.
so, you can't figure out, there's no valid relationship between x and y, because I have 2 and they're not consistent with each other. For example, at the same time, right? So this is an inconsistency. And at the same time, you might have identified a relationship, and I know this is really, basic, but it's a good way to kind of mentally consider this. 2x equals 3y and 8x equals 12y. This is a redundancy, right? Those aren't independent. Those are dependent on each other. They're the same relationship. They just look different. And so there'll be times, especially when you're looking at material balances, where you're like, well, there's 3 equations. I'm like, well, are they dependent on each other? Right? When you're looking at certain components, if I have a 2-component mixture and I have an x for N2 and a y unknown for O2, you might say, well, that's 2 unknowns, right? And 2 things to consider, but they're dependent on each other, so they're not independent, right? Because x is N2 and 1 minus x is O2. So what looks like independent variables, with further consideration, you might realize, no, they're dependent on each other. They're not independent. There's not 2 things here. There's 1, because I missed a relationship or the linkage between them. And so that's why it's important to really kind of take the time in these material balances to ensure that you don't have redundancy or inconsistency as you're identifying those relationships and equations. And so the most common sources of, those independent equations, they're going to come from your material balance. And that's kind of where the number of components comes into play, because each component can have its own material balance in addition to the total, but the total is not independent of the component material balances, because the components all have to add up to the total. So you can't just say, if, for example, if I have a 2-component stream, I don't have 3 material balances, I have 2. Even though I can write a total component 1 balance and component 2 balance, because total equals component 1 and 2. And since there's a relationship that links the 3 together, I have 2, not 3. Some other considerations, your energy balance, not for this class. That's, C308. Also, any process specifications, those relationships where I'm like a third of the stream of this just makes up that. Then you can consider, what physical property information and laws, what are the Dalton's law, Boyle's law, we'll get into that. And what are your process constraints? Those are going to be your sources of unknowns. And then finally, if there's reactions, your stoichiometric relations will become important. Any questions on this so far? All right. Let's take a look at an example. I have a stream of humid air going into a condenser to make it not so humid, which 90% of the water vapor within the air is going to be condensed and removed from that airstream. If the flow rate of condensate, which is liquid leaving the condenser, is going to be measured at 220 liters per hour, if the dry air's, or essentially the air without water, is going to be taken as a mixture of 21 mole% oxygen and 79 mole% nitrogen, calculate the gas stream leaving the condenser and the mole fractions of oxygen, nitrogen, and water within both the dry air and the wet air, humid air feed streams. So let's take a look at this problem. The first thing we want to do is make a flow chart. So this is the condenser problem. So I'll draw my little box. I'll have my humid air, dry air, and water leaving that system. So as before, I have some moles coming in and some moles leaving each system. Now what's been specified? Well, I know that in the problem statement, I have 220 liters per hour of water leaving the condenser. And I know that that water is 95% of what was in the feed. And I know I have some amount of oxygen, nitrogen, water in the feed. I'm also going to have some amount of oxygen, nitrogen, and water in my dry air. So what else am I missing? Well, I can rewrite it a little bit like this to make it more organized. Because since I have a relation for my dry air, but not for my wet, humid air coming in, I can say 0.21 N1, 0.79 N2, or N1, is my dry air flow rate, because I know the relationship between my oxygen and nitrogen in that stream. I have no idea what the flow rate my water is. I have some form of a relationship between the water in the feed and the water leaving the condenser, right? I have this 95% of H2O in the feed is leaving as the condenser. So I can say N3 is equal to 0.95 N2.
Is this based on the example 3 in the PowerPoint?
Yes.
It says 90 instead of 95. I didn't know if that made a difference.
Oh, it will make our final answer different. Thank you. I get confused. At the same time, I have no idea flow rates here. Correct. So the question becomes, how many degrees of freedom do we have?
Is the N6 not just 0.1 and 2 for the H2O?
You're right, it is. And so we can make another specification. Because if 90% of the moles are leaving in the condenser, that means 10% must remain in the dry air by the balance. So I can say N6 is 0.1 N2. Is that it? Is there anything else I can specify?
Well, none of the oxygen or nitrogen is going out with the water, so there should be the same amount.
Right, and so I can rewrite this, as kind of like I did before in that humid stream, right? 0.21 and then 4.79 and 4, right? I can bundle those in terms of one variable because I know a relationship between the two of them, and I can clean this up. That's why I think it's important to have a flow chart, because as you get more information, you can redraw your flow chart with that information, right? And so the flow chart that I had when we first started is a little different than what I have now. And it makes it a little more able to kind of manipulate without having to get lost in a bunch of calculations. You're just, you're drawing a figure and allowing that figure to evolve as you draw it out. Does that make sense?
Yep.
All right. So how many degrees of freedom do we have? Well, how many unknowns do I have?
1, 2.
Well, I'm saying
Do we have like 3?
5 unknowns. Actually, well, technically N3 is known because we have a flow rate, right?
Yeah.
So I'm seeing 4 unknowns. So how many relationships do we have in this problem?
Can you go over what the unknowns you were finding are? Because I'm only seeing 3.
Yeah, the unknowns that I don't have is N1, N2, and N4 and N5.
But I thought we have, or we have, N5 is the 0.1 and 2.
True, but that's relationship. It's still right now, because we don't technically have a value, it still exists as an unknown, if that makes sense.
Okay.
Because
Why?
then you can say, well, how many equations do we have or relationships that are available to us to solve and determine N2 and N5? Does that make sense?
Yeah, do we have to include N3 then? Because that's not like a moles per.
You can. I probably would, if I'm honest, because as I've drawn it, I don't have an N3 written, but I do have a value or variable that allows me to solve it. And so that's is why a degree of freedom analysis gets really tricky, because you kind of have the tendency to start putting things together before everything's kind of taken shape, if that makes sense, right? Because you're like, well, I do have the flow rate, so I can solve for N3, but I'm like, at the same time, if you're looking at a degree of freedom analysis, you don't have N3. What you have is a variable or a value that allows you to calculate it, but as of right now, you don't have that value. So we have, one piece of information in terms of this 220 liters per hour. We have another piece of information associated with the N3 as given. This relationship was developed from the water component material balance. So that's another relationship. And we have the oxygen and nitrogen material balances, but they're currently coupled in this problem, so they only exist as one specification. Because since we've coupled them, instead of saying N1 and N2 and N4 and N5, we really only have one. So for this problem, we only have 4 relationships. So as written, there's still 1 degree of freedom. And so there's no way to solve this problem as specified. We need to make an assumption or take some form. We need more information in order to fully specify this.
What about the number of components? do you subtract that as well?
Those are accounted for in the material balances. That's why it gets, when I say the number of components, depending on the nature of the problem, a lot of times you can just subtract it based on the number of components, but it's really fed into this independent relationship because the number of components are because for material balances you can write one for each component.
What
But
about
in this example, the oxygen and nitrogen are coupled
so
because I've
N1?
already reduced the number of unknowns by making N1 a variable for both oxygen and nitrogen. I use that relationship to simplify the number of unknowns. So I can't rely on having an individual material balance for the oxygen and nitrogen as I've written in this problem.
What about N1 equaling N4? So that would get your
That's true. But that's from the oxygen and nitrogen material balance, right?
yeah.
So from the O2 and N2 material balance, right? Since the dry air isn't leaving with the liquid, you can say that. N1 equals N4. And so you guys are on the right track, right? So you're developing these relationships based on these material balances. But at the end of the day, as given in the problem, there's 5 unknowns on the flow rates and there's 4 pieces of information that we have.
Can you
And so,
turn N5 into a component of N3? Like, you could say, I don't know, because they're both N2, and then it's just like 1 minus N3 would equal N5.
that's true. Because like we can kind of go down this a little bit if you'd like. So as we have 220 liters per hour of water, right? Which the density of water is 1,000 kilograms per cubic meter. And in 1 cubic meter, there's 1,000 liters. Right. So I have, doing this math, 220 kilograms per hour approximately of water, which I said there was 32 kilograms, actually that was oxygen. For water, there's 18 kilograms per kilomole, which means for this, 220 divided by 18 is 12.2 kilomoles per hour, right? So I can say, well, N3 is 12.2 kilomoles per hour. And I know from our relationships that N3 is 0.9 N2, right? Because 90% of the water in the feed was leaving as liquid, which implies that N2 is 13.9 kilomoles per hour. And then by my water balance, that makes N5 13.9 minus 12.2, or 1.7 kilomoles per hour, right? So I solved for N3, N5, and N2. So, this I've got, this I've got, this I've got. The problem is there's no way as provided for me to solve for the actual flow rate of oxygen and nitrogen. I'm missing that relationship.
Oh, like a mole percent or something like that.
Yes. So in this problem, there's no relationship for the dry air versus the water, right? So that's where my degree of freedom is equal to 1, and the problem is unsolvable as written, which means I need that information, right? If this was a plant and a process, I would say, well, we could look at this, but we need some sort of relationship or an assumption of that relationship to finish and make this problem fully specified. Now, for example, I could say, well, if I'm going to assume that in the humid air, the water was 12.5 mole percent of that whole stream, right? Then I can say 12.5 of N2 plus N1 equals N2, right? There, divided by 100. And I can solve with that relationship for N1. Meaning, if 12.5 mole percent of that total stream is 13.9 kilomoles, N1 then becomes 97.3 kilomoles per hour. And as we said, N1 and N4 are the same. And then once I have that, then I can say, okay, what's my dry air to humid air comparison? All right, so if I went from 12.5 mole percent in the humid air with 13.9 kilomoles per hour of water, and I went down to what it was in N5, which was 1.7, so 97.3 plus 1.7. So I went down to about 0.017. So in dry air, my water mole fraction is down to 1.7 mole percent. All right, so this relationship was needed in order to fully specify the problem and make my degree of freedom 0. Any questions on that example? Degrees of freedom analyses are really tricky. And so take your time with it and, be a little careful when you start, reaching, because, in a true degree of freedom analysis, this is useful because it's specified in the problem, right? But this is from the material balance. This is from the material balance. And so this becomes, relationship. I don't know, this isn't super. This is part of a relationship. This is a given information, right? And so all of these are useful in reducing the numbers of degrees of freedom, but it gets tricky. At the end of the day, if you do it right, even if you start going down the rabbit hole, you should end up with the same final result in terms of degrees of freedom. It's just what you consider unknowns and what you consider, equations gets a little difficult. You have to be careful that you don't go down the rabbit hole and then you start double counting things. And then you think you have everything specified when you don't. And like for this example, if you didn't do the degree of freedom analysis, you'd get, here, and then you would get lost, right? You would say, I have no idea what to do. And it's better to figure it out here, as you're doing that flow chart, before you kind of get, halfway through the calculations and realize there's something missing. All right. So is there any questions on that? So, in terms of doing this single component material balances, make sure you develop that flow chart, do a degree of freedom analysis, figure out what are your unknowns, what are the relationships and equations, material balances that I have that I can set up and solve, and make sure that if something's missing, you take an appropriate basis to get what you need from the problem. Any last minute questions?
Yes, sir. What are your office hours today?
It should be from 2 to 4. I'll try to send out an email reminder. I'm sure a couple of you might have questions as you start kind of jumping into the homework.
Yes, sir. Thank you.
No problem. Happy to help. Anything else I can do for you guys? All right. If not, you guys have a great weekend. Like I said, don't forget homework's due tonight, quizzes due Sunday. If not, I will see you guys on Monday, and we'll start jumping into a little bit more complex material balances. So take care, guys. Go ahead, Mitch.
Can you work out a problem from the book now, or do you want me to come to you during your office hours?
Let's work on that in the office hours.
Alrighty, cool.
No problem.
Have a great day.
You too. Take care.
Have a good one.
Bye.